Alright guys, we're working on a 2011 Chevy Impala. It's got the 3.5 V6 in it. And the customer's complaint is they were driving down the road, the car died, and it would not restart for them. So just some initial key on views here. You know, the engine's cold. I ran it long enough to get it in the door. I ran it off of brake fluid to get it into the shop, or excuse me, brake cleaner. But if we look at the fuel gauge, it's pretty close to empty. Not exactly on it. Let's just keep that in mind. So attempting to crank the vehicle, this is what happens. Got a little start stall there. And then we have a crank no start condition. Do that one more time. So that's what we're working with here, guys. I've already checked fault codes, did not have any in memory. So for the next step, we're just going to think about you know, what this engine needs to run. We need spark, we need fuel. I already know what this car is missing. It's missing fuel. This is a fuel system problem. To get this car in the bay, as I said before, I ran it off of brake cleaner. One thing I'm not going to show you guys is I sprayed some brake clean through the intake tube, and I was able to get the car to start up and run. So that confirms that this is a fuel issue. The next thing I'm going to do is I'm going to check for injector pulse. So here's the vehicle, guys. As you can see, I've already been doing some testing, so I kind of have a direction of where we're going, but I'm just going to show you some tests we did to get to this point. I had this engine cover off, and really what I want to do is check for injector pulse. Unfortunately, all of the injectors on this vehicle are underneath the intake manifold. We have a main bulkhead connector right here. This is going to include all of the injector feed and control wires, and this just runs under the intake manifold from the main harness. One way we could check for injector pulse is we could tie into one of these control wires with either a test light or a scope, and we could verify that we have injector pulse. Another way we could do it is where you can identify the injector fuse, and then we can just take a quick amperage capture using the lab scope there, and that'll tell us if we have injector pulse or not. Regardless of which way we go, we're going to need to pull a diagram because I'm not familiar enough with this system. So I'm going to I'm going to pull a wiring diagram. I'm going to see where injector power comes from, and then we're just going to tie into that, and we're going to get an amperage measurement of all 6 fuel injectors. That will tell us that we do have injector pulse, and we can move away from that and towards fuel pressure. So yeah, let me get some diagrams. Alright guys, so I've got some diagrams printed off for this vehicle. What we're looking at on this page is all 6 fuel injectors for this engine, this being a V6. We see this pink wire coming off of them. That is going to be the feed wire. I've just highlighted them to make it easier to view. This pink wire goes off of this page on pin number 2, and we're going to follow that over to its adjacent page, and we follow it up, and we can see that it goes to the injector 2 fuse. We also see the fuel pump relay, and the fuel pump fuse is on this page. That's pretty convenient. We're going to keep that in mind. But what I'm going to do is to check for injector pulse is I'm going to pull this injector 2 fuse out, and I'm going to put a fuse jumper in series where that fuse went, and we're just going to take an amperage measurement and make sure that we do have injector pulse, and we're going to verify that using fuel injector current ramps. So I'm going to show you the setup after I get it all set up on the car. Alright guys, so this is the setup I'm going to use. I'm tied into this injector 1 fuse, which is the power feed for the fuel injectors. I just have a low amp probe running underneath the hood back here, and that's going to my Vantage. I just have this in a lab scope mode, pretty wide time base. So all I'm going to do, guys, I'm just going to crank this over, and what I want to see is I want to see injector pulses. I want there to see repetition to them. You know, really this is just a easy, stupid easy test to see if we have injector pulse or not. So I'm just going to go ahead and crank it. As we can see by these square waves on the screen, we do in fact have injector pulse on this car. So based off of that, injector pulse is not our problem. That's not the reason this car is not starting. That also kind of points away from any sort of security issue or anything like that. So the next step we're going to do is we're going to start looking towards this fuel pump as the potential cause for this no start condition. Alright guys, so continuing with our diagnosis here. Chevy's been pretty nice to us, and they've given us a Schrader valve. All I've done is I've connected a fuel pressure gauge up here, and I'm just going to jump in the vehicle, and I'm going to attempt to start it and then take a look at what sort of pressure we have. My suspicion is that we aren't going to have any at all. So just cranking this vehicle over, attempting to start it. That should be good. Now we're going to go take a look at the gauge, see what we see. So as we can see on this gauge, we have no fuel pressure whatsoever. So definitely a fuel system problem. So our next step is going to be to start attacking this fuel pump circuit. Alright guys, so we've confirmed this is a fuel pressure problem at this point. So we want to start attacking this fuel pump as our potential cause. Looking at this pump, it has a solid ground underneath the front passenger seat, so we're not worried about that right now. What we're worried about is power feed to the pump. If we follow this gray wire up, comes over here, hooks a right, goes off the page. I have that wire highlighted here. We follow this wire over, and where it goes is this fuel pump relay. So some things we can note about this relay: we have a fuse here, and it's after the load contact of the relay. On this, we also could tell that this relay is power side switched based on this control side. We see that this one portion of this control side wire for this relay goes to this solid ground. Looks like it's above the starter motor, and this other one comes over and it probably goes to the engine computer. So we're worried about power to the pump, guys. We definitely don't have fuel pressure. So the first super easy test we can do is I'm just going to put a test light on this fuel pump fuse. And what should happen is, if the engine computer is in fact energizing this fuel pump relay, during initial key on as well as cranking, our test light's going to light on this fuse. A lot of other vehicles, they'll put this fuse on this other side before the relay switch. This test would not work on those cars, but being that this fuel pump fuse is after this relay, we can just put our test light there, make sure it lights in the crank position as well as initial key on, and that will tell us that the relay as well as its controls are all good, and then we can begin focusing more on the fuel pump itself. So that's the test I'm going to do. That's coming up next. Alright guys, so I've identified the fuel pump fuse for this car. It's this 15 amp fuse right here. So what I'm going to do is I've just got my test light going to ground, and I've got an assistant in the car. What he's going to do for me is he's going to turn the key on, and then he's going to crank the vehicle, and we're going to look for power here momentarily during initial key on, and then we're going to look for this test light to light pretty solid throughout the entire duration of him cranking it. So test light to ground, I'm just making sure it lights, and you can see it does. So I'm just putting my test light on this terminal here on this fuse. Alright, go ahead and turn the key on. Alright, so we see that initial prime event take place, and then it shuts off. Alright, go ahead and crank it. Alright, that's good. So as we can see, guys, throughout the entire duration of him cranking this, our test light was lit. We also had an initial key on. So what that tells us is, for one, this fuse is good, and for two, this fuel pump relay is doing its job. We don't need to worry about controls. We don't need to worry about the relay itself. So our next step is going to be focusing on the fuel pump as the cause of this condition. Alright guys, so admittedly, I'm pretty lazy when it comes to diagnostics. I want to get an answer pretty much as quickly and easily as possible. Putting this car up in the air and lifting it up to test this fuel pump directly, that's definitely not the easiest way to do this. So what I'm going to do to get an idea of what we're looking at with this fuel pump is I'm just going to pull this fuel pump fuse out. I'm going to put a fuse jumper in it, and then we're going to take a current measurement of the fuel pump. We're going to look at brush integrity. We're also going to look at RPM and total amperage draw of this pump, and hopefully that's going to give us direction as far as what sort of issue we are looking at. Really what I'm trying to do is I just I really don't want to lift this thing up in the air yet, and sorry about the focus issues. There we go. Yeah, I just don't want to lift this thing up yet, guys, and test directly at the pump, because that's going to take time and it's going to take effort that I just don't want to apply yet. So anyways, next check, we're going to pull this fuel pump fuse. We're going to put a fuse jumper in, and we're going to look at fuel pump current at this location. So that's coming up next. This test is pretty much the exact same as the fuel injector test we did before. Just got my amp probe going to the fuel pump fuse instead of the injector fuse. Jumping back in the car here, you can see I've got the Vantage. It's currently set up on a 5 amp scale. Let's see if I can get you guys a little better shot of that. There we go. Hopefully you can pick out the numbers. Currently we don't have any current flow. I'm on a 10 millisecond scale, or excuse me, I'm on a 5 amp scale, 10 millisecond sweep. That's how they do it on these snap-on scopes. So pretty zoomed in here. All I'm going to do is I'm just going to crank the vehicle over, and then I'm going to stop this, and then we're going to analyze this fuel pump waveform and try to determine what's going on. So I'm just going to crank it now. As we can see, we have a picture on the screen. Crank that for a little bit longer, and I'm going to stop. I'm just going to stop this capture. Alright, so I've got this capture stopped. So I'm going to get this thing set up, go back and review the data that we captured, and then we'll analyze this fuel pump waveform and see what we're looking at. Alright guys, so I've got our capture frozen here on the screen. What I've done is I've set some cursors. So things that I do know about this pump is that it has 8 commutator bar segments. So what I've done here is I've just set cursors up so we can view each individual commutator segment. This is going to do a couple things for us. One, we can look at each individual bar and just get a better idea of how the integrity of that bar is. Another thing we can do with this is we can calculate fuel pump RPM. I've already done this. The way we do this is we're going to take our delta measurement between our cursors, this 11.71 millisecond number, and we're going to divide that into 60,000. I've already done the math for you guys. This fuel pump spinning at 5,123 RPM. A little bit low. Generally on a good fuel pump on most cars you'll be around 6,000 RPM. That's with the engine running. Some other things that we're noticing here is the total amperage of this. You can see at this bottom portion of some of these bar segments, when current flow stops, we're around 2 amps, and then towards the top we're around 3.5 amps. That's definitely pretty low as far as these fuel pumps go. Generally the number I see as a baseline sort of on these GMs is around 6 amps or so, something like that. So we're way less than that. Based off of this, kind of what I'm thinking is there's a potential that this thing may be out of gas. You know, these brushes all look fine. I mean, there's definitely some sort of movement happening in this fuel pump. It's definitely rotating, it's definitely spinning for sure, but this thing's not even attempting to start. And you remember before when we looked at the fuel gauge, it was definitely at the lower end of the spectrum. So what we're going to do in lieu of this, just to rule this out as a possibility, is I've got some gas here. Hopefully we can focus on that. But all I'm going to do is I'm going to put a little bit of gas in this car, maybe a gallon or two, and then we're going to see if it cranks up. If it does, that points us away from the fuel pump, and really what we need to do at that point is address a fuel sender or fuel gauge and accuracy issue. So yeah, I'm going to put a couple gallons of gas in here, and I'll bring you guys back after I've done that, and we'll see what sort of result we get. Alright guys, we're back in the vehicle. I just put about 1.5 gallons, maybe 2 gallons of gas in this thing. We're just going to see if it starts. I'm going to turn the key on, we'll look at our fuel gauge. We can see that it did move up a little bit. So now I'm just going to go ahead and crank the vehicle. And as we can see, it definitely started. So potentially what we're looking at here is possibly a fuel gauge inaccuracy. You know, we were right above this kind of larger mark down here before. Now this could also be normal for this vehicle. Maybe that's maybe that's the normal range of the tank being empty. Really a lesson is, you know, why would you run your vehicle that low, for one? And you know, I mean, you're gonna have issues, guys. I mean, come on. But I think what I want to do at this step, being as how this vehicle does run after we put some fuel in here, is one, I kind of want to redo that amperage measurement to get a before and after as far as what an empty tank looks like in a new tank. And I'm going to do some more digging and see what a normal, completely empty view of this gauge would potentially look like. So as I said, possible sender inaccuracy, possible gauge inaccuracy. We're not sure yet. You know, it's kind of on that borderline of, you know, is it wrong or not? You know, if this thing were reading half tank and it was out of gas, then clearly we would have an issue. But being how close we were to this, that very well could be not the case. So anyways, what I'm going to do is I'm going to get reset up on this fuel pump fuse, and I'm going to redo another capture as far as this fuel pump amperage goes. And then we'll do a before and after comparison of the two. So that'll help identify these issues. All right, guys, so this is the new capture on this fuel pump current. As you can see, I actually had to adjust my scales to see this. That 5 amp scale we were on before did not work. Just taking a look at this waveform, what we can see is the low portions of these commutator bars where there is really no current flow, the pump is slowly decelerating. We have around 7 amps of current flow. And if we look at the top of these commutator segments, we have around 9 amps of current flow. So a pretty big difference as far as amperage goes, you know, almost 3 times what we were seeing with no fuel in the tank. To revisit the RPM measurement we did, currently with this vehicle running, this is 10.15 milliseconds. Again, we divide that number into 60,000, and that'll give us fuel pump RPM. I've already done that. The number we came up with was 5,911 RPM. So this fuel pump's definitely spinning a little faster. I think we can attribute that to the higher battery voltage. You know, this vehicle's running at this time. The alternator's actually charging the battery. So, but anyways, you know, we were pretty much spot on our suspicion. You know, upon initial seeing this very low fuel pump amperage, you know, it definitely sort of pointed to this thing being out of fuel. Based on the gauge position, you know, it reading so low, that kind of reinforced that as well. So yeah, definitely some really cool lessons on using fuel pump current waveforms to determine fuel system issues. So again, potentially we have a gauge inaccuracy issue, potentially we have a sender inaccuracy issue. I'm going to visit that real quick, do a little bit of digging, see if I can find some information on these gauges, and see if it may be normal for it to read in that location with the vehicle completely out of fuel. So I'll get you guys up to speed after I've done that. Alright guys, so what I've done is I've got some more information as far as this sending unit and how it works. And basically what it does is it reports directly to the engine computer. Testing these in the past, what I found that these are 5-volt pull-down sensor design. So the engine computer is going to send 5 volts, and then the sender is going to vary that voltage based on variable resistance to ground. Going through this flow chart here that I found for testing this thing for operation, I found a handy little spec here. You know, what they're wanting you to do to test the circuit is use a variable signal generator, and this 40 ohm number here, that's going to be empty. So this 40 ohm number is our empty specification. So let's keep that in mind. I don't have a signal generator, guys, so what I'm going to do to test this is I came over to my handy dandy resistor box, and I found 2 resistors, and I've wired them in series with one another to equal a total resistance of 42 ohms. And coming back over here to the diagram, what I'm going to do is I'm going to disconnect this connector on the fuel pump and sender, and I'm going to wire this resistor in series to this connector disconnected, and then we're going to look at the instrument cluster gauge to see what it reads. So that's the test we're going to do, and really what that should do is it should tell us that the sender's reporting inaccurately, and it'll also tell us that the gauge on the instrument cluster is reporting inaccurately. So that's coming up. So one thing I'm thinking about, guys, is when this vehicle came in, this fuel level gauge here, it was just a little bit above the empty mark, that bottom larger bar there. And on the DIC display, this display in the middle, we didn't have any sort of low fuel warning indicator, and that's pretty concerning. I think potentially, you know, that's an indication that we do in fact have some sort of inaccuracy issue going on here. So anyways, we're going to do that test with the resistor at a fixed resistance that we know is good for an empty fuel tank. We're going to wire that into this harness, and then we're going to see if this gauge drops down to E, and we're also going to see if we have that low warning indicator. And yeah, that's really just it's going to prove out the cluster, it's going to prove out the wiring, it's going to potentially condemn the sender. So that's what we're using this test for. Alright guys, so I've got the vehicle up in the air and I've identified this connector. The first test I'm doing real quick is I want to check this sensor ground location. I want to check that for low voltage to make sure it's good. I can't do that with this thing unplugged. So I just wanted to do that real quick before we actually do this resistor test. This is the setup up here, and this is the connector location. I just have a T-pin going into that black-white wire, which is the sensor ground location for this full fuel sender. And if we look at the meter, our current reading is 3.5 millivolts. So absolutely nothing wrong with that sensor ground. What I'm going to do with this, guys, so I'm going to unplug this. And if we look at this connector, it's going to be sort of tough to see, but right here where my thumb is, that's the signal wire for this fuel sender unit, and then the one we were T-pinned is this this wire one over from it, this black wire, or black with white wire here. That was the sensor ground. So obviously I can't do this from this connector because this just goes to the tank. What I need to do is I need to hook my resistors up there where this harness connector comes through the body of the car. That's going to be pretty tough to show you guys, but what I'm going to do first is I'm going to attempt to get a voltage measurement on the signal wire from the engine computer for this sending unit, and I'm going to show you that this is a 5-volt pull down design switch input. So let me get tied into that and I'll show you. Alright guys, so the next thing I wanted to do after testing this sensor ground to make sure that was good with this connector plugged in, all I did was I unplugged it, and I've got two leads going up there. One lead is connected to the black-white wire, the sensor ground wire for the sender. The other lead is connected to the signal wire going back to the engine computer, and this is what we're reading. Pretty unexpected. 1.98 volts on this. You know, and this would be open circuit resistance essentially. So this signal wire, basically unplugged, has 1.986 volts on that. I spoke earlier that I was pretty sure that this was a 5 volt pull down design. Typically that's what I've seen on these, but that really just doesn't appear to be the case, at least from what I'm seeing here. But let's just keep that in mind. A little worried about that, but we're going to go ahead and execute the resistor tests, just because, you know, we have good specs for those, and that's the manufacturer recommended way of testing for inaccuracies. But let's remember this 1.986 volts. This is the open circuit voltage of this signal wire going back to the engine computer for the fuel level sending unit indication. So yeah, 1.986 volts unplugged signal wire. Alright guys, so when I saw this 1.98 volt number on this fuel sender signal wire, that had me a little bit concerned. My initial thoughts were, you know, is this shorted to ground or something like that? I mean, you know, every time I've dealt with these in the past, it's always been a 5 volt pull down design on these you know, later modeled Impalas, Malibus, stuff like that. So with that in mind, what I really wanted to do is I wanted to get a little bit more information on this. You know, there was something did not seem right based on the fact that the fuel gauge reacted when we put some gas in this car. So what I have here, this is just a printout from the troubleshooter menu of the Verus, and this is a circuit high fault code for the fuel level sender sensor circuit. And all I've done was I skimmed over this, and man, this really gave me a good explanation as far as what's going on here. So if we read this, what we can see, it says the fuel level sensor changes resistance in response to the fuel level. You know, we knew that already. The ECM monitors the signal circuit of the fuel level sensor and the type of fuel, remember that, in order to determine the fuel level. Now, this is a flex fuel vehicle, guys. That's one thing we need to think about here. Let's continue reading some of these areas that I highlighted. For regular unleaded fuel, the ECM monitors a constant signal. When the vehicle has approximately 20% or greater ethanol for E85 applications, the ECM controls a pulse cycle signal where it monitors the signal and calculates the fuel level percentage only during the on pulse of approximately 100 milliseconds. Sorry about this weird focusing thing that's going on here, guys. But if we continue reading, when the fuel tank is full, the sensor resistance is low and the ECM senses a low signal voltage. When the fuel tank is empty, the sensor resistance is high and the ECM senses a high signal voltage. The ECM uses the signal circuit of the fuel level sensor in order to calculate the percentage of remaining fuel in the tank. Yeah, we knew that. The ECM sends the fuel level percentage via the serial data circuit to the instrument cluster in order to control the fuel gauge. So all of these fuel gauge controls, you know, to the cluster, they're all going to be computer controlled. But what we learned here, guys, this being a flex fuel vehicle, which I did not account for this, you know, in the variables of testing this. I thought this was just going to be a run-of-the-mill 5 volt pull down design sensor circuit, but that's not the case. What's going on here is this engine computer is actually sending a square wave to this signal, or to this sensor, and depending on the voltage level of that square wave, you know, it's going to get pulled down to ground a certain amount, you know, through the resistance of the sending unit. The engine computer is going to determine fuel level based off of that. So to make this a little easier to understand, I've kind of drawn this little diagram here. This is our voltmeter. This is that body connector that we were hooked into. You know, we were just connected across from this, across the sensor ground to the signal wire, and we were reading 1.986 volts. This was open circuit voltage level, guys. So this was with no resistance intact. This would have been the maximum voltage that this engine computer could have pulsed to this thing. And I think what was happening was, you know, if we round this up to 2 volts, you know, potentially maybe the duty cycle of this signal was 50%. So the exact same time that it's high, it's low, and vice versa. And what we were doing is we were just taking an average of that. You know, you can see this hash line. You got to remember, when you're using a digital multimeter, what it's doing is it's taking an average of everything that it's gathering. So it's not going to show you these up-down periods of time. It's going to show you the average number, which would be indicated by this dashing line here. I've just drawn this hashed line about where our multimeter was reading. Now, I'm not sure what voltage level the engine computer is actually sending to this sensor. It's possible that it's 5 volts, but you would theorize that if we had a 50% duty cycle, as in this signal's high, the same amount it's low, that we would read 2.5 volts. That's not the case. We saw 1.986. So one possibility is that this engine computer is pulsing a 0 to 4 volt square wave, you know, open circuit to this sensor signal. And that's the way it's operating. It could be 5 volts. I'm not sure, guys. I didn't get that measurement. So what this is a representation of high sensor resistance. So let's say we were up here at this 250 ohm sort of area. You know, applying Kirchhoff's law of voltage drops, if we had high sensor resistance, this voltage level from the engine computer would be high because it would have less of a voltage drop across the resistor inside of the engine computer because of the high resistance we had in the sender. The opposite would happen if we had low sensor resistance. You can see that this voltage level that the engine computer would see would be a lot lower because the resistance to the to ground through the sending unit would be a lot lower. There would be more of a voltage drop. So that gets into some a little bit of electrical theory. That's not my focus with this. What I mainly wanted to really stress here is that this isn't a typical fuel level sending circuit. Being that this is a flex fuel vehicle, the engine computer is doing something slightly different with this, and this is where this strange measurement we got came from. So now that we, you know, understand this a little bit better, and we know what to look out for in the future on these, let's go ahead and get those resistors hooked into this car and continue troubleshooting. So yeah, just wanted to clear that up. Alright guys, this is how I have this wired in here. I just have these 2 wires coming down to this resistor we selected earlier. I just have these 2 guys wired in series, and they're going up there to that connector. If we come over here to the scan tool, we're reading a pretty high number, around 90%. So that tells me we're kind of backwards of what we were thinking based off this description and operation. Having some focus problems. There we go. You know, kind of going off this, it says vary the signal generator resistance between 40 and 250 ohms. Verify that the fuel gauge displays a range that varies between empty and full. You know, I kind of interpreted that as maybe this 40 ohms would be empty and the 250 ohms would be full. I think that's actually opposite. So what we're going to do is we're going to find a 250 ohm resistor, and then we're going to wire that in series, and then we're going to see what this fuel tank level percentage number on the scan tool does. If it goes to near 0%, then we're going to take a look at the instrument cluster and see where it's reading. So that's coming up next. Alright guys, these are the new resistors I'm using. I tested these at 235 ohms. Just 2 resistors in series here, still connected at the same place. We're going to come back over here to the scan tool. Come on, focus. Focus. There we go. The number we're seeing is 5%, so I'm going to drop this vehicle down and we're going to take a look at the instrument cluster and see what our gauge indicates and see if we have a low fuel warning indicator. Alright guys, so we're back up in the car, and as you can see, we have a low fuel level warning on the dash now. And we can also see that our gauge is reading you know, just a little bit below that bottom bar there. What this tells us, guys, is this sender is not reading accurately. This instrument cluster is. We substituted known valued resistors, and we achieved the responses we were looking for. What that does for us is it verifies wiring integrity to this back to this PCM. It also verifies that this gauge on the instrument cluster is reading accurately. The information regarding this fuel level is sent over the network on this particular vehicle. So really, that's pretty much it. You know, we know at this point now that this sender, it's over-reporting fuel level. You know, it potentially has high resistance and its variable resistor in the sender unit, you know, where the little lever sweeps. It could also be a wiring problem, but that's going to be on top of the tank if that's going to be the case. So regardless, guys, this fuel tank has to come out. We learned a lot on this one. You know, this car came in as a no start, and you know, we kind of attacked it as a no start. Did some pretty basic checks to figure that out. We came to the conclusion that this thing was indeed out of fuel, and that put us on to testing this system to see if this sender and this gauge were reporting accurately. We clearly found that that is not the case. We have a known value resistor installed in series to this sending unit circuit currently, and we know that the resistance that we are using is good specification wise for what this sender should be displaying, should be reading at a low empty fuel tank level. So we're pretty much done, guys. This thing needs a sending unit. It's built into the entire assembly, so really this car is going to get a fuel pump and a sending unit to correct this condition. It's pretty good that we didn't just send this guy on the road, tell him he was out of gas. You know, this would have potentially happened to him again. You know, when this vehicle came in, this fuel gauge was a little bit above that second red mark there. You know, and we definitely did not have this fuel level low warning indicator on the dash. So good on us for recognizing that. Good on us for taking the steps necessary to be 100% on this. And yeah, guys, that's pretty much it. Inaccurate fuel level sending unit causing a stall and then a subsequent no start. So, all right, guys. Any questions? You know, just let me know. Thanks.